Alright, what I want to look at here is something called potential energy. Now, you're all used to potential energy being this formula, EP equals mgh. Now, that formula there, we can look at in terms of work equals force times distance. Force equaling mass times acceleration, which in this case is mg. Now, that's all very well when you're dealing with near the surface of the Earth where the force remains the same. But if we go a long way, the force gets smaller and smaller and smaller. So if we're going to do force times distance, the force is actually going to change during that distance change. So if we're actually going to work out the potential energy of going maybe from the surface of the Earth all the way out to infinity, we're going to have to take into account that that force is changing all the way. Now, we can do that easily with calculus. That's the good thing about calculus. Now, as we go all the way out there, potential energy is increasing because we're going against the force. If you go against the force, then potential energy increases. So we're going to define at infinity the potential energy is equal to 0. So if we say that, and that's like the most potential energy you can have, then all these other places must be negative potential energy. So these are all going to be negative EPs, right? And as you get closer and closer, the EPs are getting smaller and smaller. So the EP down here will be negative, but it's going to be smaller than the EP up here in terms of our negative, if you like. So what we want to do now is work out the exact potential energy at a place. We could say, hey, what's the potential energy at that place there? Now, that place has that distance. We'll use r for distance. That's usually what we use in physics. I know in high school we often use d. So going from that place all the way to infinity, that would be a certain amount of energy, right? That would be negative potential energy up to maximum potential energy, which is 0. That's a positive change in energy. And we could define, therefore, that energy. It's going to come out as a negative energy at that point. So we're going to have to do a little bit of calculus, nothing too horrible. We'll do an integral from r out to infinity of the force times the distance. And if we do that integral, you know how the r's are going to work. R squared is going to become r to the minus 2, so it's going to become, increase it by 1, divide by that, it's going to become r to the minus 1. So it should be no surprise. I won't do it, but it should be no surprise to you that it ends up being a negative, and it ends up being just r. So that's the potential energy, and that's the one that we need to remember. Now, we've got a formula for potential energy at that point. It was just the work equals force times distance, but we had to use calculus. Now we can look at the kinetic energy at that point. Now you're all going to go, well, we already know the kinetic energy, it's just half mv squared. But the kinetic energy I want in a similar form to that. So if we use the old v squared over r times m, which is the centripetal force, which is provided by the gravitational force, then we can start looking for a formula. Cross out the r's. We've still got gm little m over r. We can get rid of the, well, we don't want to get rid of the m's this time because we're trying to make a formula for half mv squared, and we've already got the mv squared. So all we need to do is divide both sides by 2, and we've got a formula for kinetic energy. So kinetic energy equals big G, big M, little m, all over 2r. And we already had the potential energy was minus big G, big M, little m over R. So now we can actually have a formula for total energy. And what is it going to be? Well, we've got a half positive type energy with big G, big M, little m over R, and we've got a minus big G, big M over R. So this is just like minus 1, and this is like plus half. So the total energy must be minus big G, big M, little m, all over 2R. It's the total energy. So we've now worked out a formula for the total energy of the satellite at that point. And it's negative. Now we're going to see a similar thing when we do the electron orbiting the nucleus. That's why this was so important.